Thank you, Pedro, for the introduction, and thanks all for listening and for the invitation to this workshop. So I've really been enjoying the talks here. It's an honor to be here. And today I would like to talk about generalization and extrapolation in graph neural networks, more from a perspective of trying to understand these properties. This is joint work with a number of people that I've been collaborating with, in particular, my student Keyulu, I would like to point out here. So this talk is about algorithmic reasoning. And what is algorithmic reasoning? We already saw this in previous talks. It's essentially having a neural network learn a full optimization algorithm. So questions that can come up that you're trying to learn to answer are such as, like, you're given a set of items, what are the colors of the farthest pair of objects? Or in physical reasoning, trying to predict the next state of a physical system, or trying to compute something like a shortest path. So in all of these tasks, what you have is you're given essentially a universe of some items, and they're interacting in some way. And then first you have to actually perceive these items and encode them in some feature vectors. And then you're trying to reason about these items and try to answer the question. Now, this is essentially similar to what Peter talked about on Tuesday, but different from his talk today. I would like to focus on the second part of this pipeline and trying to understand sort of how you could learn this reasoning. So what I will assume is that we already have done the perception, and we already have our objects encoded in some form as feature vectors, like maybe the colors, the positions, etc. And we're just trying to learn to answer a question. So we're essentially just learning the algorithm. And what I would like to understand here is how well can actually different neural networks learn this reasoning task, and why or why not can they? And this is essentially a question about generalization, and I would like to look at it in two different parts. The first one is looking at just the standard way of generalization. You're given training distribution, you're looking at data from the same distribution, and relating generalization performance to actually structure of the architecture and structure of the task. And in the second part of my talk, I would like to go further and look at extrapolation. So now you're seeing data from a different distribution. Can you work, will your method work on that or not? And what does that depend on? So let's start with generalization. And since graph neural networks will play an important role in this, let me just quickly recap. What is a graph neural network? I know many of you have worked on this, but I just want to set some basics that we are all on the same page. This is essentially a work about generalization analysis of GNNs, and there has been previous work on that, but that looked more from the perspective of sort of more learning theoretic ideas. So looking at VC dimension, radical complexity, or looking at trajectory based, looking at dynamics of gradient descent, and via the neural tangent kernel, how that relates to generalization. Here, what I would like to do is I would like to take into account a little more the actual structure of the task and the actual structure, the architectural structure of the neural network. So to make this a little bit closer to what's happening and a little bit easier to interpret. So as I said, let's first start with a brief recap of graph neural networks. So graph neural networks are a powerful method to encode graphs or subgraphs in vectorial form. And they're essentially learnable message passing algorithms. And this is essentially an important perspective for this talk. So we start out with each node having some features. And if you don't have features, it could be constant. And then we go in rounds. And each round essentially corresponds to a layer in my neural network. In each round, each node in parallel collects the information, meaning the features from their neighbors, and combines it with its own information to update its own representation. And this is called the aggregation step. And this is essentially a multi-set function. So just a function that takes a set of vectors and aggregates it into an output vector, which is combined with the current representation of the node. And this combination is essentially usually just some sort of weighted combination. And what you're learning in these networks are the aggregation operations and the weighted combinations, if you do that. and the final readout, meaning now you have learned for every node a representation, and now you want to collect these representations and put them into a final vector representation for the entire graph. And this is essentially, again, like an aggregation operation. So something like transforming these vectors and summing over them, for example. So as a concrete example of an aggregation function, just to make it a little bit more concrete, because it'll be very important, is the following form. That is a sum aggregation. So you apply essentially a neural network or some nonlinear transformation to the features of each of the neighbors individually. And here we combine it with a feature of the center node. So you could do something like a comparison or pairwise reasoning, and then you sum up the outputs of these MLPs. And the W here is an edge feature that you could also take into account. So you're learning these MLPs. Okay, so this is our graph neural network. Now, how does this come into reasoning? So now let's go back to our algorithmic reasoning tasks, and let's see what kinds of neural networks we could put for this reasoning network and how their properties affect what they will actually learn. So now I would like to focus on this part. And I already started with graph neural networks, but per se, there's no obvious reason why we should even use a graph neural network. We have this collection of items, a collection of representations. What should we use? And so let's go like sort of from simpler to more complicated architecture in some ways. So the first attempt would be to just use an MLP, a feedforward neural network, fully connected. And I just concatenate my input features. Of course, this has several drawbacks, as you may imagine. This is not permutation invariant. It doesn't actually take into account that this is actually a set and not a specifically ordered set of items. So we could instead use a set function. So this is an architecture that has been proposed especially to learn set functions. And the difference is that we first apply an MLP to each of the items by themselves, sum that up, and then apply another MLP. So this is permutation invariant by nature. And then an additional approach that people have tried is to actually use a graph neural network. And the idea is that if you don't know an underlying graph structure, you make a fully connected graph, and then you just use a graph neural network on that fully connected graph. And what you will get is essentially this aggregation functions, which are shown here, which do essentially a pairwise MLP on the node whose representation we update and the neighbor nodes. And eventually this is the readout step. So we have three different architectures, and this is essentially a structured version with little MLP modules built into it. Now, all of these, if you look at just representing set functions that are permutation invariant, all of these networks can represent the same thing. So any function that one of these networks can learn, the others can also learn. However, if you actually train them on these reasoning tasks, you will see big empirical differences in their learning performance. And the question is, why does that happen? Now, the main idea is that what we are actually trying to learn are algorithms, and these neural networks are implicitly already proposing a computational structure, and there must be some relation. And we are not the first ones to actually have thought of that, but so far it's mostly like a vague notion of, okay, there's some kind of inductive bias that this works. And we would like to make this a bit more formal here. So the main idea is that algorithms are really structured arrangements of subroutines, and many of the reasoning tasks are essentially algorithms, like computing a shortest path. Now, neural networks also are essentially a structured arrangement of learnable modules. So in our graph neural network, you could say each of the aggregation functions is a module. And now, if that matches in some way, then we should be in good shape. Now, this is the inductive bias, but can we formalize it? And the way we formalize it here, first the informal version is via what we call algorithmic alignment. And we say that if a network can mimic an algorithm via a few and easy to learn modules, then it should be able to learn the task well. So if you think about, for example, shortest path algorithm, if I can mimic that algorithm by learning a few simple modules by taking my neural network and each of the MLPs learns a simple function, then I am aligning well and I should be in good shape. So let me make this a little bit more concrete. And here is actually a shortest path algorithm. This is the Bellman-Ford algorithm that you may have seen in an algorithms class. So what does it do? It goes in k rounds, and in each round, for each of the nodes in the graph, it updates its state. And the state of the node in this case is just the distance to the target, the currently known best distance to the target. So you basically, what it does is each node looks at its neighbors and looks at, if I would go via this neighbor, would I actually get a shorter path to the target? And this is provably correct. Now, if you look at a graph neural network and look at sort of just putting these next to each other, it looks actually very similar. It also goes in iterations, and each iteration is a layer. And then in each iteration, I update the representation of each node. And the way I update is by doing this MLP on the node and its neighbors, essentially, and then summing up. So now if I basically just in this MLP learn this Bellman-Ford update step by basically taking a min over the neighbors, then I basically have mimicked this algorithm. So this, all I really have to learn here is a min and a linear function in my MLP. And this is fairly simple. So what we would expect is that a graph neural network can learn this to mimic this algorithm well. But say a deep set architecture would have to learn the entire for loop in one of these MLPs, which is much harder because there's much more structure it has to actually extract. And likewise for the MLP. So we would expect that they would not learn it as well. Now here's some empirical evidence for this. So this is on relatively small data, but just sort of as a proof of concept, we trained these different architectures on learning a variant of a shortest path. It's a little bit more complicated. You have to learn the edge weights, but it's essentially that. So you see that the MLP and deep sets really don't generalize well, but graph neural networks, and the number here is the depth, once they are deep enough, they actually generalize well. But you have to go deep enough. And now the thing is, in these instances, the shortest path was typically at most length 7. And you see actually here, like once you have 4 layers, you're in good shape. Now Bellman-Ford itself wouldn't do it in 4 iterations, but if you actually do a bidirectional version of Bellman-Ford, you can do it in 4 iterations. So this very well matches sort of this hypothesis of the algorithmic alignment. If you take this further, you can actually get sort of a hierarchy or classification of different reasoning tasks and try to predict what kinds of architectures would actually work well by doing this notion of algorithmic alignment. I can show you that table later in the break if you're interested, but I would like to look at alignment now a bit more generally, more from the perspective of GNNs. And if you actually think about the GNN architecture, it essentially is very good at mimicking a large number of dynamic programs where we have a state, and the state is essentially the current feature representation. And it's updated by doing some simple operation on each of the neighbors, maybe a comparison, maybe a simple transformation, and then aggregating that. And so here, the modules I'm talking about are essentially these aggregation functions, the MLPs and the aggregation functions. And that if they can mimic the DP update, then I'm in good shape. And the feature vector is the state in the dynamic program. And now the nice thing is that many algorithmic and physical reasoning tasks are actually dynamic programs, like predicting the next state or doing shortest path, etc. Now, this is very nice. And how can we formalize this a bit more? I had promised you, okay, we'll try to formalize it. So the way we formalize it here is by relating it to a PAG framework. And we say that a neural network, M epsilon delta, aligns with an algorithm if it can mimic the algorithm via n shared network modules. So this would be basically n different MLPs here. And each of these MLPs learns a simple function, and then you can mimic that task algorithm, an algorithm that solves the task. So now this is PAG learn. So here the notion of simplicity is essentially that you can learn essentially that the DP update in this case with a very small number of samples. So it's a simple function like a min or a linear function or something like that. Now, if this actually holds, so if basically you can replace your modules with easy to learn functions and you have an algorithm to solve the task, then you can also learn well. And you can actually also make this more formal. So here's the theorem that says essentially if you have this alignment, then your neural network can also efficiently learn the task that you're interested in. So with essentially the same number of samples. So this makes a number of assumptions. The strongest assumptions of these is maybe that you need a little bit more supervision. Essentially, in each layer, you need a bit more supervision. But actually, there have been works that do exactly this training and practice. In our experiments, we didn't even do that, but we observed the same trends. So this shows you now like empirical and theoretical evidence that this algorithmic alignment is a good formalization of this notion of inductive bias, and that it helps you in generalization. Now, next, I would like to take this one step further and look at extrapolation out of the data and distribution that you have observed so far. And what will be important for this is not only the architectural structure, sort of this arrangement of small computational modules, but also the nonlinearities. So what do I mean by extrapolation when we think about learning, for example, graph algorithms? So the idea is that I train my model on a set of graphs, maybe small graphs, but I would expect that if I actually learn, say, a shortest path algorithm, it should also generalize to larger graphs and graphs with different degree distributions, etc. Now, does that actually happen? This is sort of the ideal case. It does happen actually in some cases. So this is results from prior works that show that with graph neural networks, actually there are cases when you can successfully do this. However, if you look at, say, feedforward neural networks like MLPs, they often fail out of distribution, meaning they don't do what you would ideally like them to do. Now, this is a bit of a contradiction because at the end of the day, I just told you that graph neural networks are essentially a structured arrangements of these MLPs. So MLPs are really the modules in my graph neural network that I have arranged. So how can I generalize with graph neural networks out of distribution, but MLPs can't? And under which conditions can I actually do it? So to understand this, let's look at how do actually MLPs generalize out of distribution first. And here is a very simple experiment. So we have one-dimensional training data. You see this sine curve, that's my training data, and I'm looking only in this blue box. So I have training data in a limited range. And now I'm training a ReLu feedforward neural network on this. So since this is a universal approximator within the training data, if I have enough training data points, it's going to perfectly approximate my training data. Out of the training this data, what you see is that you essentially get this linear extrapolation. And now this is maybe not so surprising. After all, I have a ReLu network, and that's essentially what the ReLu implements. This also happens in higher dimensions, and what it looks like is that you're essentially getting piecewise linear, like basically directionally linear extrapolation here. You can also formalize this. So this theorem is by looking at the NTK regime, that basically as you go away from your training data, you quickly approach actually a linear function in any direction. So what do we get from this? Essentially what this says is that ReLu neural network really away from the training distribution, away from data that it has seen, all you can really expect it to do is learn a linear function. And if it has enough data, you can prove that it will actually learn sort of the correct linear function if the underlying function is linear. But beyond that, it's not so clear. After all, it hasn't seen any data. So what does that actually mean for our graph neural networks? So let's go back to the example of the shortest path algorithm. where what we actually learn is this dynamic programming update, basically a min over the distances of the neighbors. So this is the cost of going to the neighbor, and this is the cost of the path from the neighbor to the goal. Now I said, okay, graph neural networks align well with that, because if you look at this sum aggregation, I look at my MLP, essentially all I have to learn is this min and a plus. And I can easily learn this with the MLPs. So now,
Stefanie,
however,
I think you have 5 minutes left. Just to,
okay. You know. Okay, that's good. So we have this MLP, and we said essentially the green box has to mimic the purple box. And this is fairly easily doable if you're within distribution. And the MLP, however, has to learn a nonlinear function. And now what I said to you in the previous slide is that if you go out of the training distribution, what you'd like is, or all you can really expect the MLP to do is learn a linear function. Now, here you would run into trouble because you'd just be summing up over essentially some function of the distances of the neighbors. Now, if you actually look at papers that did successful extrapolation with GNNs, they use not a sum aggregation function, they use something else. You can do other things than sum, anything that's permutation invariance. You could use a max or a min. If you use a max or a min, all your MLP has to learn is a linear function. So here, this also aligns well with the dynamic program, but in some sense even more, because all you have to learn is not even a linear, simple nonlinear function. All you have to learn is a linear function. So now if we think of that and connect it to the example of the ReLu networks, what would we would expect is that for interpolation, it doesn't matter. Like you could use either of the two green boxes, but for extrapolation, you want something where you only need to learn a linear function, because that's the only thing you can sort of reliably learn away from the training distribution. Now, this is our hypothesis, and we call this the linear algorithmic alignment, so that basically you can mimic an algorithm by learning simple linear functions. And the hypothesis is that this will actually help extrapolation. Now, let's look at this empirically. So we have a proof also for simple cases that this actually holds. Let's look at this for shortest path empirically. And now I have two different regimes. I have the interpolation regimes, where you basically get data that looks dissimilar to your training data, meaning in terms of the size of the graph, the degree distribution, the node features. And you get extrapolation, where all of these are different. Now you see that if I use max or min pooling, both of these errors are actually low. I'm performing fairly well. I'm extrapolating well. If I use sum pooling, I'm interpolating well. I have good test error on data that looks like the one I've trained on, but it doesn't look very good if I go away from that data. So the extrapolation doesn't work. So this is further empirical evidence that this hypothesis actually is useful. Now, what does this actually mean? It means, well, if I want my network to generalize out of the distribution, I have to somehow do something that all I really have to learn are these linear functions. And the way you can get at that is to essentially encode the nonlinearities elsewhere from prior knowledge. So I could either do this in the architecture as I did here, so replace essentially the sum with a min or a max, like adjust your aggregations, adjust essentially the way you're the way you're arranging your modules. The second thing is about the features. So we also looked at this for physical reasoning, where basically you can sometimes replace nonlinearities by having nonlinear features. Where do you get them from? Either you know it, or maybe you do some kind of pre-training that gives you more meaningful features that are more applicable for a wider range of data, and that can also help. So that's the way, so like from this perspective, that's the way to go if you want to extrapolate. Now, if you actually have this linear alignment, do you generalize? You can under one more condition. So here's this one more condition. It's a condition on the training data. Essentially, you need enough information from your training data to know that you want to learn a linear function. And this example basically shows it in terms of the distribution of the structure of the graph. So here we tested on general graphs, but we trained on only graphs of a specific type. And you see that for certain types of training graphs, actually, you don't extrapolate well, even if you have this linear alignment. So, and it's maybe reasonable if you only train on path graphs, all the degrees you ever see is like 1 and 2. So it's not very meaningful. If you train on a complete graph, the shortest path is not so meaningful, etc. So there are conditions on the training graphs as well. And in simple cases, you can even formalize it. So this is a lemma that basically formalizes it for learning max degree. It says essentially you look at for each of your training graphs, you look at some statistics of the graph, like the max degree, the min degree, and how often that occurs. And now you take the collection of these description vectors, and that should span R4. So this is basically your distribution of graphs has to be rich enough. So with these results, I would like to conclude. So I showed you ideas about generalization within and out of distribution for graph neural networks, for algorithmic reasoning tasks. And I believe that many of these notions also actually apply to many other tasks as well. So just to have within data generalization, algorithmic alignment is very useful to have, and it essentially formalizes inductive bias. Second, if you want to generalize out of distribution, the nonlinearities matter too, because of the way your modules actually are set up, because of the way ReLu networks actually act out of distribution. So here it's better to encode the nonlinearities in the architecture or features, as we have also seen in previous talks. If you want to know more about these details about these works, I'm citing our 2 iClear papers here, where we can read up many more details. Thank you.